We use a Vicon motion capture system to do barbell tracking, so your typical sort of barbell kinematic analysis. And then we also use a markerless motion capture system that we've just recently acquired, and we're still trying to figure out how to best use that. But so we have multiple cameras that take digital video. We take those videos and run them through AI-based software that then helps us automatically digitize the lifter's body positions.
Hi, Kristof. It's my pleasure to have you in Evidence Strong Show. If you could briefly introduce yourself, that would be awesome.
Yeah, no problem. Hi, Alex. I'm excited to be here and chat with you today. My name's Kristof. I'm currently an associate professor at Marquette University. Some of my teaching responsibilities here are in scientific principles of strength and conditioning and sports biomechanics. And some of the research work that I do focuses on weightlifting biomechanics specifically. A little bit more on my background, I guess, and how I got into this. I used to throw the discus and hammer in college and a little bit post-collegiately. And as part of that, weightlifting was always a big part of the training process. And then once I sort of finished my track career, if you can call it that, I got connected with some friends at a local weightlifting club and sort of fell in love with the sport. Had an opportunity to work on a research project with a friend during undergrad, and things sort of snowballed from there.
Awesome. So today we'll be speaking about your current work with USA Weightlifting and the testing you do for the national team.
Yeah, no problems. When we have the camps at Marquette, again, the athletes will fly in. So it's sort of like a training camp. They get to stay in a hotel, work out on campus. We've done typically between 1 to 2 days of sort of full testing, running different protocols. Some of the athletes will have DEXA scans to look at sort of lean body mass distribution, or some of them maybe body fat percentage. So that's typically done as first thing in the morning while they're in a rested state and fasted state. And then the first day of testing, we will do some vertical jump assessments. The athletes come in, do the regular warm-up as they prepare for sort of what we call quote-unquote heavy singles day. So this is where the athletes will come in and go through their almost competition-like warm-up, and where we take them through a sub-maximal to close to maximal progression of lifts in the snatch and then in the clean and jerk. And again, that's sort of preceded by different jump tests. We're very fortunate.
Sorry, do you prescribe their warm-up, or they do what they would normally do?
They do what they normally do. And so, I mean, one interesting thing about the way that USA Weightlifting works as an organization at that level is that it's a decentralized system. So each athlete has their own personal coach. Some of the coaches will travel to the camp with the athletes, and they'll sort of, again, it's primarily athletes. It's athlete center, right? In the sense that the athletes really, we try to get them to do what they need to do to be right in top shape so they can perform heavy lifts on the platform. So we try to prescribe as little as possible. Ideally, we just say that we would like to have them do maybe between 3 to 5 close to maximal single effort lifts. All right. So if that's a series of 85, 87.5, 90, 92.5% of their 1RM, something like that, where they get close to their competition maximum. And we do that for the snatch and for the clean and jerk. And I was just going to add that I think we're pretty fortunate because we have Mike Catone, who's the high performance director for USA Weightlifting. He will sort of run it like a competition. So he'll solicit what the lifts will be for each of the athletes, and he has them warming up and really again, runs it like a competition. He's like, hey, you're athlete X, you're 2 out, right? Where are you at? You're close to ready. And we literally just sit there and record data. So it's great fun.
What data do you record?
Yeah, so during the heavy singles, so on that first day, we record data from the motion from the force plates, bilateral force plates, so we're able to get gram reaction forces under the left and right foot. We use a Vicon motion capture system to do barbell tracking, so your typical sort of barbell kinematic analysis. And then we also use a markerless motion capture system that we've just recently acquired, and we're still trying to figure out how to best use that. But so we have multiple cameras that take digital video. We take those videos and run them through AI-based software that then helps us automatically digitize the lifter's body positions. And so in all, right, that gives us a really nice complement of full body kinematic motion analysis data, ground reaction forces. I should say the markerless motion capture system also gives us left and right joint angle data. And we overlay that with or combine that with the barbell tracking data. In a very general sense, we look at barbell kinematics and some barbell kinematics and joint kinematics. So on the barbell kinematic side, we do look at barbell trajectory. We also look for some asymmetries left to right in terms of barbell sort of rotation throughout the lift. We'll look at the kinematic pattern. So what is the barbell velocity profile and the barbell force application profile? And we do that both in terms of, when I say profile, not just peak velocities, which is pretty commonly done, right? So like peak second pole velocity, for example, or first pole, second pole velocities, but we'll also look at the pattern more dynamically as time series. And so we typically divide the lift up then into sort of beginning of pole, first pole, second pole. It's interesting that we notice that less and less lifters exhibit a sort of quote unquote classical transition phase with the rebending of the knees or velocity drop during the transition. But then second pole into the we call turnover phase, so from peak vertical velocity to peak negative downward velocity after the barbell reaches maximum height, and then throughout the end of the catch phase to when the bar gets turned over, right, either overhead in the snatch or the shoulders at the clean, and reaches zero velocity when the bar comes to a stop, essentially. So we'll look at that profile very dynamically, the sort of temporal sequencing throughout that, and most of the work sort of is focused traditionally on, I think, pulling mechanics, but we're trying to dig into a little bit more into what's happening during the turnover phase. What are the temporal dynamics of that? How long does it take lifters to reposition themselves in space? How much work do they then have to do, and how much forces do they have to produce to overcome that downward momentum of the barbell? Because something that I'm sure most of the listeners are probably familiar with it. In most cases, when lifters miss, right, it's not, some of them don't complete the pull, right? They will quote unquote clark the bar, but most lifts will be missed from an overhead position, and so sort of looking at turnover and catch mechanics is something that we're definitely interested in as well. So that's the barbell trajectory, some of the bar kinematics. As I said, we also look at barbell force application. So as a percentage of barbell load, what is the percentage of force that's being applied to the bar throughout the different phases? And that's actually something that I find quite interesting, because I don't think if you ask the person, how much force do you think you have to apply to the bar to snatch 100 kilograms? Is it 130 kilograms of force, or is it 150? I think there's just very little information out there in terms of normative data for that. So that's something that we've been sort of developing alongside of this, is trying to create more of a normative database so that we can then say on par or on average for this sample of lifters, this is what we see, right, as an average lift. And then if somebody deviates from that profile to some extent, right, if there's a very large spike in force application during the second pull, there might be, right, I guess it sort of leads us then to ask a little bit more questions as to why is that happening? Does that have something to do with the positions that they're in, or how they're approaching the lift from like the perspective of the intent, or how they think about the pulling technique per se? And then since most of those quantities or those variables that we talk about, like velocity and forces, are vectors, we also look at sort of not just the magnitudes of how much force is being applied, but also the directions. So how does the force application direction align with the trajectory of the bar, to see how much, if there is a lot of sort of horizontal motion or forward hipping of the bar, how much of that leads to in a really unscientific way, like a force loss or an energy leak, if you will, how much force could be, instead of directing it forward, how much of that could you redirect in the vertical direction to perhaps lift more weight rather than accelerating the bar in a bad direction?
How much of differences there are in general in all of these variables from athlete to athlete?
I think that's a really good question and really interesting. We haven't really done too much athlete to athlete comparison in the traditional sense of looking at, running t-tests or looking for differences between groups of people. Most of the analyses, because the reports that we generate are very athlete specific, it really just focuses on each athlete as their own, as an individual. And so it's more of a within subject analysis to see. A good example, I guess, would be barbell trajectory, right? So there are some analyses that we do where we take the overall trajectory, the entire time series data, and we run it through this sort of algorithm that calculates the amount of variation that happens due to certain factors. we then look at how do those factors correlate with things like load, for example. It's the main one. And so we're able to then say for athlete X, right, as load increases, we see this change in the pattern and the trajectory. And that pattern, right, might account for, let's say, 95% of the variation in their overall difference in all the trajectories that we record for that person. So if that's all related to load, that gives us an idea of, okay, as load increases, this person sort of, I like to think of this as like dials the knob, right, or switches their techniques. I don't want to say actively switches, but they adapt in a certain way, and that's just one dial that gets adjusted. And if that's right, if that accounts for most of the variation, then that's pretty good. Sometimes we have some other athletes where there might be two dials. One is related to load, so that's good. Another one that we can't quite, it's not correlated to any of the variables that we measure or that we haven't quantified yet, right? And then that sort of raises an interesting conversation. It's like, why do we think that athlete has this variation that creeps into their trajectory as they increase load, but that's not explained by load? So is it something additional, or is it just their sort of trial to trial variation? If that is excessive variation, maybe that's related to maybe some slight instability in their technique. And then we're also able to parse out where in the trajectory that stability occurs. So is it during the first pull, is it during the second pull, or the turnover phase? So again, we primarily do that for each athlete individually. We haven't done it for the entire group yet. Yeah, more to come. One of the things that we did recently as well is that we went to an actual weightlifting competition. So we took some of our equipment on the road, so to speak. And so that's something else that we're actively mulling over, that I think the environment that we have in the weight room is pretty good, right? In the sense that we don't have to put markers on people. The athletes can lift the weight as close to competition as possible, but obviously there are lots of other factors in competition that might influence how somebody performs. And so taking some of the equipment on the road out to competitions, I think would add an additional element to some of these analyses as well.
What competition was it? Was it a local meet or?
We went to the North American Open Finals Championships in last December 2023. And so, yeah, I mean, it's an open competition, so you could go through and see who the top lifters were at that competition, but it definitely included some who were on the U.S. national team who had competed on world championship teams. So that said, we recorded data from all A sessions. So I think it was 19 sessions that we collected, 3 snatches, 3 clean and jerks. This is a lot of time spent pressing buttons and recording, but I think it will give us a really good broad data set, because again, there are some Olympians in some of those groups that definitely sort of runs the range to then high national level lifters. And again, I think with a sort of perspective of developing lifters and seeing what the variation is, I think they'll be really, really good.
Will you publish this data?
Yeah, I think for that, we do have sort of aims to publish it. And actually the 2 graduate students that I alluded to earlier, they're sort of actively trying to work through digitizing some of that data and sort of in the process of preparing some abstracts at this point.
Amazing. We'll be waiting.
I want to say in some of the sessions, some of the lifters, you have quite a bit of variation. Even though you're in a weight category, there are variations in body dimensions among some of these lifters. And so that's something of interest to us, where we're sort of hoping to be able to calculate segment lengths as well. So to get an idea of lower body segment lengths, femur lengths, torso length across the different weight categories. And so, right, if we do see differences in sort of pulling technique or kinematic variables, looking at if and how that correlates to body segment parameters would be interesting. One of the other projects that one of the grad students did is that there are some weight categories where we actually have males and females, or right, like the 81K class, I think we have both males and females. And so it makes for a really interesting comparison between sexes, right? And because you're matching for body mass, presumably muscle mass to some extent. And then, there's also the 55K as well. And so we have like a heavy match, a smaller match of weight classes. And so just to get an idea of, right, is there other differences in pulling technique or pulling kinematics, turnover, catch, whatever, right, variables. I should say I work with several researchers who they focus primarily on sex differences and physiology, etc. And so whenever we present this data, they're always like, do you see any sex differences? And so we're sort of gearing up to be able to say, in fact, yes, we've looked at this. So.
Oh, exciting times coming. I will not ask you about the particular setup for this competition. I hope you will publish the data and then I can lure you in to talk about the specifics. Okay, so we covered day 1 of testing. What comes next?
Yeah, so then the second day we've sort of reserved for, I guess sometimes we've referred to as quote unquote capacity testing. Capacity in the sense of isometric pulling strength, dynamic pulling strength, and in some cases also some upper body pressing strength. And so there's different ways that we assess that. And so we've done isometric pulling assessments at the start position. So some people use the isometric mid-thigh pull. We use an isometric pull from the start position. We feel like it matches the overall conditions a little bit better to weightlifting because we were matched directly for velocity right at zero. So things that we know influence force production, like force velocity, force angle curves, or force angle properties, I guess, things that influence how much force somebody can produce are matched almost one for one in that setup position. So we look at how much force a lifter can produce, and we then map that onto how much force they are actually producing when they're doing the lift.
They can't hide.
Yeah. Another one of the tests that we do on the second day is to do our dynamic force velocity profiling test. And so it's either for the clean pull or the snatch pull, where the weightlifters will perform up to 2 repetitions of the respective pulling exercise with anywhere from 80, 90, 100, 110 to 120% of their 1RM for that specific lift. Again, they're doing the lift they're doing the pulls on the force plate. And so we're able to calculate average ground reaction forces, we're able to calculate then average system velocity. So the velocity of the lifter and the barbell as a system together. And we also use the bar tracking. So we're able to calculate average force applied to the barbell and then average barbell speed. And with the average force and velocity values from either the ground reaction forces or from the barbell directly, we're able to then map out a force velocity curve for each lifter. Those force velocity curves, I should say curves are actually lines, so they're not your traditional curvilinear force velocity relationships where they're the lines. We're able to fit a line to it, and we can calculate sort of what we would estimate their theoretical maximal force would be, or their theoretical unloaded pulling velocity. So those variables gets a little esoteric, but in a way, again, we're able to get an assessment of their dynamic pulling performance. And so we combine that with, again, what are they actually doing when they're lifting, 95% of the 1RM, what would they be capable of, which those sort of calculations of theoretical values would give us. And then from there, and I think, again, it's an interesting sort of thought experiment to just think of, okay, if you wanted to lift a certain load, how much force would you actually have to produce, right? Granted that the average velocity will probably have to stay the same. And so what would be the increase in force needed? Are you there, right? So we've certainly had some athletes who are able to produce way more force than what we see. I guess when I say way more force, we look at the average, for example, isometric pulling force that somebody produces with respect to the force that they produce during a 1RM, right? Some are way above that average. So it seems like they have more left in the tank, that they're not using all of their pulling strength, whereas some athletes tend to be below average. And for some, we also see that like at liftoff, they're pretty much producing almost near isometric forces. And so I know you had a question in the ones that you sent out in terms of some of the conversations that we have with coaches, right? And then you can probably imagine that this leads to some conversations around what sort of, whether, I guess there was an increase in strength or pulling strength that needs to be addressed, or if where the athlete is at with respect to their training year or their training cycle, I guess.
So the conversations with coaches, are you able to say, hey, this athlete needs more strength training, this athlete needs more speed training? Are you at this level of advice?
In a way, yes. Sometimes maybe. So it's a really difficult question to answer in a way, because I think what we try to do is just present the information to the coaches. I think ultimately the coaches still have to be the decision makers, and they know their athletes obviously far better than we do. So we try to just make this part of a conversation that's ongoing. And so in a way, right, we can say that what we see from the athletes that have come to the camp, if they're Olympic or national caliber athletes, that most of the athletes will require X amount of isometric strength to perform their lift at a certain ratio of pulling force to isometric force. If somebody is really, really close to the isometric maximum, right, we would say it seems like they are below. They're really, really close to their capacity. So some strength, right, especially position-specific strength, might be something to think about. With the dynamic force velocity testing, we get similar information that if we look at the average force velocity profile, again, for most of these, right, for a pretty robust sample of elite level lifters, if somebody's force velocity profile is geared more towards the velocity end, where they seem like they're able to get moving pretty fast when they're performing their lifts, but their force side of things seems to be a little bit lower. That might be similar indication of more strength might be needed. Dynamic pulling protocol, I guess, gives us a little bit more information throughout the entire lift, whereas the isometric assessment only gives us an idea of what is happening at that point in time. So I think there are some conversations that we've had around those. So yeah, strength versus power, some specific position strength, perhaps. So those are some examples. During one of the camps, or in preparation for one of the camps, we were thinking of could we adapt the same sort of force velocity profiling for an upper body exercise. And so we used a similar sort of idea where we had athletes do push presses across different across the loading spectrum, and we wanted to map out to see what their sort of force velocity characteristics during a push press look like in comparison to their jerk performance, or how they perform the jerk. And an interesting piece there actually was that for some athletes we got very nicely sort of textbook fitted force velocity curves, right? And so again, if we look at average pushing force, average pushing velocity, there was a stereotypical force velocity trade-off. For some it didn't quite look like that at all. But then when we looked at the actual curves, the ground reaction force curves, for example, we did notice that there are almost distinct ways that people perform the push press. So some will, as load increased, will just use a more aggressive drive, for example, right? So the rate of force development increases, they reach higher peak forces, whereas others pretty much hit the same amount of overall force, but they will increase the duration over which they drive. So it's just a different strategy to create impulse, essentially, as a product of force over time. And then it allowed, right, we're able to look at an individual's sort of strategy of how they produce force and overlay that with how they are then performing the jerk.
Have you found that one of the strategies correlates better with the jerk performance?
I wish I could give you a very direct answer. The problem is that it's a very small pool, right? So it's very difficult to run correlations. But I mean, what I will say is that, and sort of it'll depend on the athlete too in terms of how they jerk. But from one sort of just general perspective, the strategy of reaching only the same amount of force and then just pushing for longer isn't really feasible for jerks in competition, right? Because you can't just keep pushing. There's a time constraint that you have to, right? You only have so much time because you have to drive the bar up, you have to reach a certain velocity during the jerk, and you have to then be able to reposition yourself under the bar to catch the bar or to lock out the bar overhead. And so in some cases, I think then it's more so that if an athlete uses that sort of time strategy to increase impulse, they might potentially run up against an issue where they can't keep pushing indefinitely. And so that might suggest that increasing force, right, has to be one of the considerations. And the nice thing is with the force plates, and so one very sort of clear instance that stuck out is where we had an athlete who just seemed like he was below average. And so if you take that then and say, well, you can't indefinitely increase the duration, you need to increase the force. Your concentric force seems like it's pretty close to what we see for average, but eccentric force isn't. Again, that seems like we're able to whittle down the sort of perhaps direction of where the coach might be able to intervene with certain exercises or overloading certain parts of a movement and strengthening certain aspects.
That's awesome. So we covered day 1, day 2 that's it, that you do only 2 days?
Yep, only 2 days. And that gives us more data than what we know what to do with.
Yeah. So 2 days of testing. Now, how long does it take you to go through all these data and produce the reports for coaches?
Most cases, I think we can put together a full report within a week. It sort of depends on the motion capture, the barbell trajectory data, the ground reaction force data. We're able to turn around fairly quick. The data files for that are pretty small. And as I said earlier, we've sort of developed our pipelines now that we're able to process that fairly quickly. Marco's motion capture data takes quite a bit longer just because of the AI software has pretty large computational requirements, so it takes a long time to process single trials to get them to be automatically digitized. And really, I think most of the time, the sort of, when we try to jump on the calls with the coaches and the performance staff, it's really just, I think we try to turn it around pretty quickly, but most of the scheduling issues just occur because we're trying to get a lot of people on the same call at the same time. And so I think that's our biggest time constraint at this point.
So you alluded to it a little bit. How then you present the data to the coaches? Do you have like a overall presentation or one-on-one? So how do you go?
Yeah, so we have group calls with the coaches, staff from the high performance staff from USA Weightlifting, and we've generated a sort of a slide deck in PowerPoint where we just drop in figures and videos and try to take everyone through like the analysis that we do, some things that we find, some things that seem interesting to us. And it's definitely been an evolving process, right? We started this 3 years ago, not really knowing what, as I alluded to, or we had some idea in terms of what people have done in the literature. We've certainly done some research here at Marquette too, and that's sort of the go-to where you start there, but then coaches will have different questions and they're like, oh, what about this sort of, can you look at this for the jerk? We say, sure. Something that we add, and then the second time, some more in-depth jerk analysis, for example.
Do you have any things, because you have an experience of 3 years of data collection, any huge surprises?
Yeah, I call these things that make me go, make me wonder. Again, I think there are some groups that have looked at catch mechanics for weightlifting exercises or weightlifting derivatives, and we've been involved with some of that work as well, but something that I still think I didn't really appreciate as much as that when we look at some of the ground action forces or barbell forces, peak forces during the catch phase, especially for the clean. I mean, peak forces are up to twice barbell weight, which is quite significant, right? So if you have, down to your 49 kilo female who are lifting twice body weight, then it means that you're essentially breaking 200 kilogram front squat, or, on the heavy end for some of the males, if you're cleaning over 200, that means that you're breaking a 400 kilogram front squat. So those values just, I guess it's one thing when we do this for sort of weightlifting derivatives in groups of, I don't want to say recreational athletes because that's not the case, but they're sort of non-weightlifting athletes. Right, the forces are, again, quite significant. So that's something that I've sort of been mulling over in terms of what that means for the overall load that athletes experience. Another interesting thing, I think, again, oftentimes we talk about peak velocity during the pull, right? I think that's sort of a variable that a lot of people hang their hat on. Certainly a variable that's very popular to get from velocity-based training methods. It's something that's pretty easy to get at. But in almost every single case, your peak velocity, right, is not enough to move the barbell to peak height. And so what I mean by that, I think oftentimes we think of, right, you reach triple extension, you finish the pull, the bar has a certain velocity, and we almost treat it like a projectile in the sense of that velocity has to be sort of enough to then allow you to turn the barbell over, right, to sort of quote unquote float up, but that's not the case. So that velocity in some cases will only get you 78 or 80% of the height after the pull, which means that the lifters have to do additional work on the barbell. And I think it's sort of intuitive in a sense that lifters or coaches know that the athletes have to be pretty aggressive in terms of pulling themselves underneath the bar, active pulling underneath the bar or staying connected to the bar during the turnover phase is actually what allows them to produce that additional amount of work on the bar. And so that's something that I'm sort of interested in trying to quantify that. What happens with that across different load? Does that differ between athletes of different, I say, skill levels, right? Or different strength levels, if you will. Yeah, so in essence then, if you're only looking at peak velocity, you're probably missing one piece of the puzzle. And so things like what will be the velocity needed to move the bar to turn the barbell over, something that will be of interest. Something also when we're looking at jerk mechanics, I sort of mentioned that we do find different ways that people sort of organize, or the different strategies that they use to produce impulse. In those analyses, also something that has sort of come out is that, when similar to the snatch and the clean, where we look at peak velocity at the end of the second pull, in the jerk, right, peak vertical velocity is reached basically at the end of the drive phase with feet still in contact with the ground, or at least one foot still in contact with the ground. And so in a way that then, since, right, you're basically done driving, you reach peak velocity, ensuring peak peak velocity is important. So finishing the drive is very important. And I'm probably not saying anything new to anyone, but when you look at the way that the data lines up, I think it just underscores that leg drive is super important. And really anything that happens afterwards, so if I'm trying to frame this, I guess in a way, it just illustrates that the legs are probably more important than what I would have anticipated. As we think of the jerk, it's sort of you probably need some upper body strength to perform the movement, but you don't really seem to use a lot of that strength to drive the barbell up. You need the strength to catch the barbell, if that makes sense.
Yes.
There is some additional work that the athlete does on the bar to reposition themselves under the bar. And so again, that's something that I think we're trying to look into a little bit more, because that's potentially then upper body strength needed to continue pushing on the bar. But really, if you're reaching peak velocity at the end of the drive, you're like, okay, so then is that it, right? It's just my legs. My upper body doesn't really do anything during getting the barbell overhead, which is sort of a simplistic way to think about it, but maybe not that intuitive for everyone.
All very, very exciting. So do you think you need another year to be able to talk about it with more data support?
What data are we talking about specifically?
Yeah, it's a big question. Sorry. The things you said you're excited about, and then you said some of them you are kind of still guessing. So my question is how much longer we have to wait for you to be able to say that's how it is, or that at least in these athletes, that's what we observe.
Yeah, most of our work that we do, or the time that we get our work done, is over the summer. It allows us more time to focus on research, where it's not as much teaching that we have to do. And so it could be shorter than a year, or it could be 6 months or so from now.
Okay, so do you have anything to say about the relationships you as researchers have with the coaches, and how many useful your work is to the coaches? I assume that it is. If you have athletes coming back, you probably are of use to the coaches. So what is it that makes it so, you think?
Yeah, I think we would like to have a very good working relationship with all the people who come, right? I think we try to, first and foremost, we try to look at this as a service that we provide to be helpful to the athletes and the coaches, and really try to downplay the research side second. And so that's why I said we do notice things. We try to make some progress on small research projects or individual sort of research questions, but most of the time is sort of spent focusing on generating reports and trying to make interpretation useful for coaches. And that's been a big learning curve for me for sure as well, coming more from the traditional research side. And here's a lot of cool and shiny figures, right, that some of the coaches may or may not find useful, or may not resonate with them. And then depending on their expertise or their background, they might find useful to varying degrees, if that makes sense.
Yeah.
One thing that I have mulled over more, I think, again, in that sort of learning experience, is that I heard this said at a biomechanics conference, that nobody likes to be told that they're wrong, right? And so I think that's one sort of lens of how we've tried to look at these things, that when we present data back to coaches, it's like, this is not us coming down or on you or the athlete and saying this is wrong, this is right, but like, here's the information, here's the data we collect. We try to compare it against, on average, right? What do we see? There's something that sticks out to us, we try to point that out, and we try to do it in a collaborative way. And even, small things that we've done from the first time through, where it's really more for better or worse, it was maybe more of an academic presentation of like, here's what we find, right? Even beginning some of the conversations with, so what are you guys currently trying to work on? And seeing if that matches or meshes with some of the things that we find with some of the coaches who then do come to camp with the athletes, right? It gives us a really great opportunity to interact with them as well, in between everything that's going on, I guess. And so being able to chat with them and build those relationships, I think, is very helpful as well. So yeah, I think we like to think we try to do the best we can, and as I said, and try to do this in a collaborative way with certainly the high performance staff for USA Weightlifting, coaches, just trying to help the athletes out.
Okay, I have two short questions then. The first one is, what is your favorite color?
Really tough question, and the sort of totally geeky answer I give whenever this comes up, I say octarine, which is the color of magic. So if anybody reads the Terry Pratchett Discworld novels, they will know, and that's my answer to that one typically.
Awesome. The last question is, if people would like to contact you, ask you some questions, or just find more about your research, where they should go on the internet?
Yeah, so I have a Twitter/X account, I guess, MU Sports Science. I typically try to do mostly professional things on there, but we do share some of the weightlifting work we do. I have a ResearchGate account where we try to share most of our research findings, but otherwise, if somebody wants it, they can just get a hold of me via email, kristof.kipp@marquette.edu. I like to think I'm pretty easy to find on the internet if you just type in my name. And yeah, always happy to chat with people about weightlifting.
Thank you so much, Kristof. It was a pleasure.
Yeah, no, this is fun. Thank you, Alex.